Yeah, let me just start over. So yeah, this is Bosamiya from CMU, who will be talking about verified sandboxing in F star. Um, Feel free to unmute if you want to ask a question in the middle, or feel free to also type a message in the chat or raise your hand, and then I'll moderate that. So yeah, take it away.
Thanks for the introduction. So yeah, today I'm going to be talking about some work that I've done over the past few years on sandboxing the execution of WebAssembly code. Uh, so this was a paper that was accepted and presented recently at Usenix. I'm going to start off with a very quick overview of the two different compilers we have in that work, and then I'll dive into specifically vWasm, which was the one that was written in F star. So at a high level, we need sandboxing since there's untrusted code everywhere, and we somehow want to be able to manage that untrusted code. And specifically with this work, we're looking at intra-process sandboxing, which means we want to be able to place multiple sandboxes in the same host process and mediate any interactions that the untrusted code in the sandbox has through only trusted APIs. Specifically here, we care about the safety, but also secondary and important goals include performance and ease of use. And on the web, there have been folks who have thought about similar ideas for a while. And this is where WebAssembly was born. Its specification promises lightweight, safe, and fast execution of untrusted code on the web. And due to this, there have been a huge number of compilers that people have developed over the past few years to compile from a large collection of languages to WebAssembly. And then a single compiler or an interpreter for WebAssembly is sufficient to give this sort of narrow sandbox, which allows you to get sandboxed code execution. And what folks realized is that this sort of property is useful even outside the web, and WebAssembly is quite useful as an execution mechanism. Despite the name web in its name, it is useful beyond. However, the promise of WebAssembly specification is only as strong as the implementation. And indeed, there have been compilers, there have been bugs in a whole bunch of compilers and where the sandboxing behavior breaks down and thus attackers could get in. So with this work, what we did is we explored two distinct techniques to achieve provably safe sandboxing. The first one is what we implemented in F star. It's called vWasm, where the V stands for verified. It's a formally verified sandboxing compiler where, of course, we have machine check proofs of safety. With our Wasm, we are able to push the performance further without the tedium of writing formal proofs. We still get provable safety. I'll briefly talk about our Wasm a little later. vWasm itself, you guys all know what formal verification is, so I can skip this. Just comparing a traditional and sandboxing verified compiler, a traditional compiler of the CompCert or KML style, it shows semantic equivalence between its input and output code. What this means, though, is that safe input code becomes safe machine code. However, it says nothing about unsafe or malicious input code. What we want to do with sandboxing verified compilers is that safe code must stay safe, but even unsafe or malicious input code should get turned into some sort of safe machine code. So our top level theorem statement, this is of course simplified, and I'll actually dive into the code a little bit in a little bit. So we don't need to focus on the code itself here, but the high level statement is that if the output code starts from any okay state and then runs for any number of steps, it should still stay in an okay state. And okay here means that only explicitly allowed behaviors have happened so far in the code's execution. And due to this, we are able to show that this prevents out-of-bounds memory accesses. You don't write to read-only memory. You don't call unsafe APIs, and so on. The proof itself is for the sandboxing pass itself is about 3,500 lines of code and proofs. And the full compiler ends up being about 15,000 lines of code. It contains a whole bunch of scaffolding and the framework to actually get to the point where you can do the sandboxing and then jump ahead. So we'll get a chance to dive into the code in a little bit. The high-level proof sketch is that we first show coarse-grained control flow integrity, which allows us to have runtime checks that cannot be bypassed. And these runtime checks make sure that all of the different constructs of WebAssembly are always maintained within bounds and you're not doing anything bad there. And we do this with a statically sized compile time sandbox. However, as you notice, it takes about 15,000 lines of code, which led to this idea where what if we could get away with not even needing to write those sort of proofs? And this is where vWasm comes in, where our insight was that if you take arbitrary untrusted code and lifted it to any type or memory safe language, then compiling that code, you get all the properties that the type or memory safe language provides. Specifically here, you can get sandboxing out of the memory safety. For predictable performance, we focused on Rust here, which is where the R in the vWasm name comes in. And thus the memory safety of Rust itself is what provides us the safe sandboxing for free. And the SFI checks for the same WebAssembly constructs could be optimized away at compile time whenever possible by Rust-C. When it's not able to optimize it away, it leaves them in as runtime checks. It also allowed us to explore static and dynamically sized sandboxes and so on. We also got the opportunity to explore runtime extensions by easily introducing inline reference monitors, tracers, sanitizers, and such. I'm happy to talk more about vWasm at a later time. We can skip the compilation example there. We did some performance benchmarks on standard WebAssembly benchmarks. And here we're looking at a normalized slowdown against native code execution. We notice that the interpreters that we compare against are fairly slow, and vWasm, the verified compiler, outperforms them consistently on every benchmark. However, vWasm is slower than basically everything else with everyone else. It trades blows depending on the particulars of any specific benchmark. In terms of a qualitative comparison, vWasm is formally verified with a more traditional TCP. However, we stick to a specific architecture, x86 in this case. However, since it's written in F star, we can extend it by adding more properties and see and try to prove more things about the output that it produces. However, vWasm, since it depends on Rust, we get this portability across architectures. We get better execution speed due to all the optimizations that have been poured into Rust-C and LLVM. We also get this ability to easily introduce inline runtime extensions. And overall, you can see the trade-off in terms of time taken to actually implement this. It's about 2 person years and 1 person month. So all of our code is available online, and high level, we think this is a really interesting space for further exploration. And that high performance and strong safety are not necessarily mutually exclusive. So that was the high level overview. I know I kind of rushed through that. However, I did want to give more time specifically for the for diving into vWasm itself, the F star bits. But any questions yet? Sure, Nick.
It sounds really cool, Jay. Looking forward to learning more about it. I'm wondering, are there no other production quality WASM compilers in Rust? Is yours the first?
So it's that's a good question. It's been a while since I took a look at all the others, and I remember at least parts of some of them do include Rust. I don't know if it's any of them are Rust by themselves. The vWasm doesn't gain its security properties just by being implemented in Rust, but instead because it lifts the WebAssembly code to Rust. So it does essentially an embedding of the unsafe WebAssembly code into safe Rust code.
I see. It's a shallow embedding of WASM in Rust. Is that the one way to understand it?
Yeah, it's mostly shallow, because of course there's some constructs where you need to mess around a bit, but it's a mostly shallow embedding, yes.
Interesting. Okay, cool. Thanks.
Cool. So I guess we should dive into vWasm then. And hopefully that's at a size that's visible to everyone. Okay, so I do have a bunch of topics we can talk about. I'll just go through them in order and see how far we can get. First off, this was a project that I started. Oh, Emacs is going mad. It's just opening everything in the universe. But this was a project that was started quite a while ago, and we kept up with updates in fstar up till a certain point. And then as we were finishing up the project, we decided to freeze the version of fstar. So what I'm going to be talking about here is not necessarily the latest fstar. I do have the version number written down here. So we froze it last February of 2021. So it's only going to include changes until around that point. So in terms of project management, I decided to come up. This was, again, early on. There wasn't any clear specific standardized way of managing a large project. And I'd expected this to grow over time, and thus decided to come up with an entirely new way of managing fstar projects, which is kind of distinct from others, which I think is a little bit interesting. So I do want to dive for a short while there.
So Jay, I have a question. I was trying to find this raise hand gesture for some time, but I could not. So you said you froze the fstar version at some point. Just curious to know, you froze it because upgrading was hard, or you just froze it because you thought, okay, we are going to not even try at this point, or just because they were like, your code was breaking a lot and it was not possible?
That's a good question. This overall tended to be less of an issue as time went. I think we were having more issues with stability earlier on, and then fstar has gotten more stable over the years. So and plus our project over time became more stable and was less fragile to things. But nonetheless, at a certain point, we decided to freeze it, mostly so that we don't even need to ask the question of fragility there. Again, we kind of wanted to get the project done. Every once in a while, it's fine going and fixing up any issues that we were seeing. Similarly, we even froze the version of Rust and so on. It was mostly just a way of making sure we get to the finish line. Not have any sort of instability around the way. Good question, though. So yeah, the project itself is managed as a whole bunch of different directories, and within each directory, there's a whole bunch of FSD, FSTI files. And the way we've done it is you just need to include makefile.dir if you just want to invoke every directory, every subdirectory, and makefile.ver if you want to verify every file in that directory. So I'm not going to dive into the actual makefiles there, but I do want to bring up this interesting piece here called parse f*args, which jumps over to the git root, picks up the f*args file, and figures out a good series of arguments to pass to f*. And what this does is it lets us perform includes all across the project, have a consistent thing showing up on every file. And I also set up their locals, which again, I'm not going to dive into the code itself, but this magically lets Emacs pick up the exact same config that was being passed to the f* on the terminal, so that we can never have a disagreement between the two. I don't believe I've seen any real disagreement. The f*args itself shows up as a nice series of just arguments specified overall for the project. It's just include all of these things. It allows you to pass nice comments into things, so you can manage this well. And we do turn off a few warnings. I think this was one of the things we had to expand over time as we were updating stuff. We did get more warnings in. Oh, and everywhere we're using a low value of fuel and iFuel, as everyone eventually ends up doing. So let's jump back. So again, I can talk a lot more about what's going on there, but just high level about the project, that's what's happening. For the
that's cool. I just to jump in there, I think this kind of thing is really useful. I wonder if there's a maybe worth starting a discussion on GitHub or something about standard ways to manage projects. And I think many people could learn from or learn from your scripts, and even just use them as is, perhaps.
Mm-hmm. Yeah, I think they should be mostly usable as is. And yeah, having a standardized way of managing projects does make things nice. I think most languages end up eventually having a standardized thing, except C and C++ for whatever reason. So diving a bit more into vWasm itself, the vWasm code, of course, we need to start off by parsing WebAssembly. WebAssembly is a binary format, and at the time, Quacky Ducky and Everparse and such were a thing. I don't believe 3D had even begun at the time when we were starting off with the parsing here. So all of this is the old Quacky Ducky based Everparse style of parsing. Unfortunately, Quacky Ducky itself was not expressive enough to fully handle the complexities of the binary format. So instead, what we do is, using the WebAssembly binary toolkit, we actually parse into a text-based format and then serialize that back to a format that Quacky Ducky can then understand, and then pass it into Quacky Ducky, which is fairly indirect, but it was what seemed to make sense at the time, and it worked out reasonably well. The Quacky Ducky based parser, of course, generates a whole bunch of FSD, FSTI files, which we compile down to .ml. But the way we did it, Quacky Ducky takes as input these .rfc files, which, if folks haven't seen before, looks fairly similar to C structs and unions. It's like C-based data structure. It's the sort of file that you would see in an RFC, an internet RFC. However, we wanted a little more templating over it. So we decided to use the C preprocessor so that we can just throw in things like hash define. And this is the sort of thing where the official WebAssembly spec requires LEB128, arbitrary sized integers, but we end up parsing and then serializing back to a direct uint32 so that we can actually use Quacky Ducky. Again, I could dive into the code a bit more, but the interesting bit here is just having the C processor allows us to write these specs quickly. In terms of fun stuff that makes F-star sad, I don't know if this has been fixed up since then, but at least as of Feb 2021, this enum is absolutely large. It's very massive, which expands out to an F-star sum type, which F-star is not particularly happy about and slows down, which is why we have serious amount of caching of F-star executions, and the parser, once it's done running, we try not to run F-star on it again, so that we're not waiting for a few hours. I believe it was a few hours at some point. I don't remember how the performance changed over time.
Just on that one, it used to be that F-star took very long on big inductives because it was generating a bunch of proof obligations for the auto-generated projectors and discriminators, each of which resulted in SMT queries. But
I see.
But I think Asim did some work recently to change that so that they don't produce SMT queries instead, and instead are done using a tactic, done using returns clauses.
It's done using returns clauses, but you can also, there's also an attribute that you can add if you don't want auto-generated projectors. So you can, but I don't know, in this case, maybe like, since it's Quacky Ducky, it may not be possible, but yeah, as Nick is saying, it may be faster now.
It may be. I don't know if it will definitely be, but there's a chance that all these SMT queries, if you are indeed being slowed down by the large number of SMT queries, then that should have been improved.
Interesting. This would be a good test case to just.
So Jay, actually, maybe you can send us this type definition in an F-star file. We can try.
Yep, we'll do that.
Okay, thank you.
I'll do that. Yep. Cool. That's the parser out of the way. And of course,
actually had another question about the parser. Sorry to just jump in, but
no, feel free to.
I guess all of this is the parser is not part of your the runtime, right? This is, you don't care that it's the performance of the parser doesn't matter too much. Is that right?
That's correct. The performance doesn't matter too much, and I mean, we still want our compile times to be reasonably fast, so that we're not, waiting too long. And I'll talk a bit more about performance a bit later. We can move that up front as well. But the performance of the compiler, like the specific case we're looking at is ahead of time compilation, where you probably want to compile once and then run, thousands of times. So unlike a JIT compiler where compilation time also is absolutely critical, for us, we're willing to give up compile time if it gains us other things.
So in your performance benchmarking that you showed us earlier, that does not include the time to parse?
It does not include compile time or time to parse.
I see. Although I guess
just pure execution time.
Because a typical scenario for WASM is that your WASM is the format of the mobile code that you're trying to run, right? And so you have to parse it, type check it, compile it, and then start executing it, right?
Yes, but again, that's the typical web-based behavior. These days, people are using WebAssembly for things like, running stuff on the edge. They're just using it as a portable assembly. So they send stuff over to the edge and then just have it execute on all those nodes there. in which case people are willing to have very long compile times as well, as long as you get fast runtime there.
Okay,
So
thanks.
good question though. Cool. So diving into the semantics of we use throughout our compiler. In contrast with traditional compilers like Concert, we actually don't really need to implement a specification for WebAssembly semantics or indeed any of the intermediate languages. Because we're only doing, we only care about the output code. The high-level theorem statement was only the output code must remain safe, independent of input code. And thus, we don't actually need semantics for WebAssembly. Nonetheless, our initial goals with this project were to also have, the traditional compiler correctness theorem along with the sandboxing theorem. There is some amount of support working towards the traditional theorem. So we do have semantics for WebAssembly implemented in F-star. We also implemented a family of intermediate languages because doing the compilation in a single step is very difficult. So it's much easier to do it as an entire pipeline where each step does one small change. But to make that easy, we implemented a family of ILs, which we call CFG-based family, since it depends heavily upon having an explicit control flow graph. And using that family of ILs, you can then instantiate it with any particulars of the IL you care about. And indeed, the final x86 code is also just an instantiation of that IL. So diving a bit into that there, the control flow graph IL looks a bit like this. So any intermediate language needs to define what valid registers are for both integers and floats. It needs to define what instructions are supported there and how to evaluate instructions. And having a printer also helps for debugging. And other than that, with just a small number of instantiations, they gain the ability to talk about a full control flow graph over things, including calls and returns. Since we also need to compile through slightly different control flow graph properties, we actually do include slightly different versions there. For example, there's call and high call, and the specific IL can decide it does not care about that specific control flow graph instruction. So this allows us to have fairly smooth, similar code throughout the compiler without needing to worry too much about changes that, without needing to have large bits of code that literally map A to A, B to B, C to C. For the most part, we can just directly reuse. So this design of abstracting that out really helped. So specifically, once we've defined this common control flow graph, we can then, for example, this is the entire definition of x86. After that common control flow graph, we just define a specific ordering of registers because we do need to care about the ABI, since this is going to be linked with other code. But after that, it's just define what the maximum numbers are, which allows us to define what valid registers there exist. And this is just boilerplate that re-exports everything by filling out the above details. So this allows us to have convenient to use semantics. Any questions about that? Oh, I should mention they're small step semantics. Yeah. Okay, let's dive into the compiler then. So the compiler itself.
Actually, Nick has a question on the chat.
Oh, sorry.
Oh,
so I can.
Yeah, go for it.
No.
I just didn't want. I thought there's some questions we could leave for the end too. So
shall we leave that for the end then?
Yeah,
I do want to get to some of the other bits as well. And see if we have time. Cool. So the compiler itself, we have a collection of different passes in the compiler. We could probably name some of these a little bit better, but we take the WebAssembly code, change that over to simplified WebAssembly, which we then change from the stack-based architecture that WebAssembly has to an infinite register-based architecture. And then we perform some optimizations. We have a conversion from the infinite register architecture to finite registers, since x86 unfortunately only has a few registers. And then we perform some amount of sandboxing on it. And we do have some common bits that can be used by everyone. And finally, do-all is the large catch-all wrapper that is, that's the main entry point that is invoked by the OCaml driver. The OCaml driver is a small little bit of OCaml code that just jumps immediately into F-star. So the one we'll be focusing on today, of course, is the sandboxer. And let's jump directly into the high-level theorem statement. This main function is basically covers the safety properties that we provide, the sandboxing safety property. Specifically, it takes a module. A module here contains the CFG-based code, as well as a few other auxiliary details around things like, here are where the functions are, here are the sort of indirect jumps that could occur, and so on. And then it takes an erased state and an erased integer, where it shows that if you start from an OK state where for the instruction pointer to be OK, you just need to be in the CFG somewhere. There's a property we call safe call stack, which is shown to be true, which is trivially true if you have never executed anything in the WebAssembly module yet, and is just an invariant that is maintained over time. And a few other simple properties, like your memory sandbox size is at max a 64-bit integer and is at least 8 bytes in size. Then what we show is that executing n steps, where again n is this arbitrary input we take, then every step along the way has been OK. And since n is arbitrary, we cannot represent infinity, but and any arbitrarily large thing, it works, which means any step along the way executing further should remain safe.
Just curious why you take n as a parameter rather than quantifying over it in the post condition.
That's a good question. It would initially start with it as a quantifier, and that made some parts of the proofs unwieldy. I mean, generally quantifiers make things a little bit unwieldy. So at the highest level, we could potentially just expose this as a quantifier and perform a small little change at the interface level, but we didn't. We thought that was trivial enough that we could ignore that one change. It is practically equivalent, right?
Yeah, fair enough.
Do you mind showing where okay could not be okay? Like where okay is
what are
modified?
the other kinds of okay? Just so I can jump there. So we have a collection of different possibilities of okay. So mem failure implies that at some point you tried to access memory that you should not have access to. AST failure is just a compile time. This was just garbage. It isn't even a valid graph. For example, or you're trying to access, you're trying to call a function that doesn't even exist, and so on. And runtime error is to try to catch the few things that aren't memory failures or AST failures, but are still valid runtime errors. For example, say you tried doing okay, I'm actually blanking on that. I'll get back to that in a little bit. I can jump through the code and find the other runtime errors, but
I guess my high level question is more like, so you have like a, in Ghost, you have like a evaluation function that steps through your state. And this evaluation function is like instrumented to like do a number of checks, right? Okay. That makes sense.
That's correct. So sorry, I don't have it immediately up here to show, but indeed, the evaluation function stores that in the state. And essentially, we have this, the only way you can stay okay is if you were okay and you continue to be okay. And due to that, any error propagates till the end of time from there. So the evaluation stops if it hits any of the failures. So evaluating any number of steps from there just stays at the same state. Good question.
So Jay, I have another question on the theorem before we move on. So what about the property that the sandboxing is not changing the like what the function is computing, what the program is computing? Like it's
the semantic equivalence.
Yeah, exactly.
Yep. So that's a good question. And again, we were initially hoping to also prove that at the same time. But getting to this point itself took, as I mentioned, about 2 person-years. So we decided we'll punt that semantic equivalence property for now and get to it later. Again, we have the framework set up to be able to slowly prove that, but this property is strictly distinct from the traditional compilation property of semantic equivalence. So here we're only talking about the x86 code not breaking out of its sandbox. So indeed, a perfectly valid compiler by this exact specification is you output nothing. It just immediately returns, right? It does nothing.
What I was also thinking. That
would be valid. Yep. So what we have is we show that on. So this is not a verified property, but this is a validation. Sorry, we have a. We performed some amount of assurance through writing a fuzzer that explores all the semantics. And we also checked on a bunch of real-world examples and showed that it works fine. So we have a fuzzer that explores semantics and performs self-checks that the semantics are valid. And we actually found a collection of semantics bugs that way. I can talk more about the bugs themselves.
It's fair, like you show that using empirical evidence that it's not just trivially satisfying this theorem, it's doing.
Yep.
Okay.
Yeah, so we're able to take images, compress them, decompress them, and so on. It's able to do big things as well.
Okay, thanks.
I'd like to jump in and just say it's 12:14. So if you could wrap up in the next 5 or 10 minutes, and we can have some discussion afterwards as well.
Okay, cool. In that case, I will skip the OCaml runner and talk about the next bits. So the layered effects, we actually use layered effects pretty much throughout the code base. The first one is for fallable compute, which is just code where you could have execution that fails, and we only want to reason about the successful execution, and the failure we just want to throw a compile error. For example, say we get completely unreasonable inputs from the user. We want to complain and just throw that away. So we ended up using layered effects for that. It's otherwise essentially a pure function. It's just making it more convenient for us to write that kind of code. So for example, in the sandbox, this sort of code, it doesn't matter what it's actually doing here, but here the ensures is ensuring things only when things are successful. And thus we can completely ignore any cases where things fail. So if we say fail with, we can just have things jump out quickly, and we no longer need to reason about them. So that was really useful pretty much throughout the compiler. Specifically for the trusted printer for x86, we defined a separate layered effect as well to make things, again, easier to manage so that the printer is a lot cleaner, even though this particular file looks a lot scarier, especially for people who haven't seen layered effects before. But roughly speaking, it's a state monad plus a freshness monad plus a writer monad, all combined together, so that anytime we need a new identifier, we can just pull out some new freshness. We can maintain some amount of internal state, and we can write it all out without needing to form absolutely massive strings. It all gets stored as a nice little list, and then finally, when getting printed, it just loops through the list. When getting printed by OCaml, it just loops through the list. So this ended up extremely convenient, and layered effects made the overall compiler writing experience way nicer. I think we initially began without it, and it just became much nicer. And in terms of the performance of the compiler itself, initially the entire compiler was written in the pure tote effect, and this, of course, we're only left with like functional lists, which if you're appending to functional lists, that's going to be slow. So what we did is we came up with wait, it couldn't find that file. That's weird. No, I'll just jump to the file. So why is that blob main thing there? Common append optimized list. There we go. So an append optimized list is just, it has a very similar interface as the standard functional list. However, internally, it's relatively lazy. If you say append two things, it just stores an append node and essentially becomes a tree. And when you need to finally merge it all together and get a list out of it, at that point it goes and merges it. And we ended up writing proofs which included to list, off list L is L itself. So this gives us a round trip conversion. And pretty much every other function, the length is equivalent to the list length if you were to convert the append optimized list to a list.
Just jumping in, we have one question from Tahina about how you extract the layered effects.
Good question. The layered effects are just they're being used just to wrap up stuff around tote and pure. There's not much else happening. So when we say reify, it's able to expand that out. It compiles and runs fine. I don't know if that's a bad idea. It worked. We tested it on small examples. It worked, so we decided to use it for larger stuff.
And the follow-up question is if this still works. Yeah, but we could maybe talk about that offline.
Yeah. I don't know about it, whether it still works. This is Feb 2021. It worked. So, and yeah, things like length and append and so on, we show that equivalent. And we actually did this. We built this quite late. We just wanted to get the compiler working before we started, optimizing the compiler itself. But writing something with the same interface and writing these, ensures things where they're shown to be equivalent meant that we could just swap this out wherever, and most of our proofs just worked perfectly fine. And we just got essentially performance for free. So overall, having this sort of design is quite nice. I don't think we can fully express normal functional lists with this implementation. I think there's a few operations that would end up extremely slow for normal functional lists, which is why I am not yet suggesting this should be taken up and just be made the default for F-stars lists. Because it's just different performance properties. If people are willing to have the slowdowns on those particular things, then it's fine. But yeah.
I have a few, if we want to wrap up, I have a few like more general questions about the project.
Mm-hmm.
So the first one is like, vWasm is slower than rWasm, right? So that means that vWasm is doing slower things. So like, what are the general things that rWasm is doing that's actually slower? Oh, sorry, that's actually faster than vWasm. Like, what is the performance differ?
So that's a good question. So vWasm is a compiler that we wrote ourselves, start to scratch, which means any optimizations that exist are only optimizations that we've introduced. And we have a very small number of optimizations in there. We use just a slightly smart register allocator. We use, small amount of peephole optimizations and such. But basically, we have no compiler optimizations in here. On the other hand, the rWasm side, it lifts it over to Rust, and then the Rust compiler jumps in, which has had, like a forever amount of time of optimizations built in. It depends on LLVM itself, right? And LLVM has had a tons of optimizations built in.
Yeah, and that's suggestion from Nick is, did you consider emitting to another tool chain like LLVM instead of straight to x86 to pick up those optimizations?
That's a good question. We did consider it. It's kind of a trade-off, right? For the vWasm side, if we were emitting to LLVM, we need to spend time modeling the LLVM semantics and then include LLVM also into our TCP. For vWasm, since our aim was we want to directly reason about the code and like give highest levels of guarantees we can about the sandboxing of the code. Like having full control over the x86 is really useful. And that's the point we took in the trade-off space. I agree that there's there's other points in the trade-off space that are compelling for different reasons. And there's a lot of interesting points to be explored.
Any other questions? Well, one thing that I think would be interesting is in these like larger scale F-star developments is to kind of pick out in your like, in your top level repository, pick out the proof developments that you think could be reusable in other projects. Because it seems like a lot of this is pretty general purpose. Like if somebody else wants to do like a Wasm project, I'm sure a lot of this could be reused.
Mm-hmm. Yeah, that's a good point. And even outside of Wasm, like the append optimized lists, they can just directly be picked up into other projects if you want those kind of properties. The layered effect stuff, assuming it still works on latest F-star, is also, I'm hoping it works, but maybe it might need one or two minor tweaks. It's, again, really useful to just have a clean thing working there. So.
I have a question. Did you, I didn't see in your list a formalization of the WASM bytecode validation, like the type checker. Is there one?
Not in vWasm itself. So we just run a separate validator that someone else has written.
I see. The theorem does not depend on the input being type correct?
Yep. Our theorem is independent of input. So we run someone else's validator just for, just for sanity checking that, people aren't throwing us absolute garbage. But we don't really depend upon it being type safe input.
Just one quick question for you. So you mentioned it was about 2 person years of development effort for vWasm. Was there like one or a small piece of that tended to take up the bulk of the effort, or how is that effort kind of divided amongst all this work you all did?
Good question. So the 2 person years includes the essentially like n different rewrites starting from scratch, because we build all the way until a certain point, and then we realize, oh, this particular fundamental decision we made early on needs to be revisited, and doing a rewrite of this entire thing is going to be easier than trying to hammer that one decision back. So a part of it was, just us not being compiler developers itself. I think that plays a part of the role there. But of course, the sandboxing, took a non-trivial amount of effort. The proofs for sandboxing, it was the main theorem after all, right? And trying to make sure everything, works and goes through there. So I didn't get a chance to dive in there, but the proofs using tactics is basically all in the sandbox. And like tons of careful normalization and rewriting, just to make sure everything manages to go through. Good question.
So I can ask a question. So like these proofs in the compiler tend to follow some structure, right? For every step or for every node, you establish some property. So did you figure out some proof patterns? Like, for example, I don't know, one trivial thing you could do is hoist every case out. And then in the big switch case function, you just call those individual lemmas. And that may be, so are there these kind of patterns that you figured?
Yes, so we did something like that. So when we're looking at the instructions itself, I don't know. add is a bad one to search for. It makes it harder. If I could. Oh, yep, things like this. So we ended up we ended up defining something called tag of instruction. So we can collect a group of similar instructions together and then prove some properties about that particular instruction. And here in this case, we know the proofs are going to look very similar. So we even define a common, compile inst t, which if I the compile inst t is going to show this. It doesn't matter what's exactly being shown here, but we collected all of that up. So we're proving that compilation property on the move zx style instructions altogether, and then on the move sx style instructions altogether, the I32 unary operators together, and so on. And then that goes and gets collected all together later on, somewhere here. Yep, here's the big collection statement that just calls out to every single tag. The reason we need to do stuff like this is it's possible any operand to an instruction might include a memory access. So we need to make sure that the sandboxing for the memory access is done right. So thus we need to actually dive into every single instruction. It's possible a different encoding of the instructions might have been better. So we do have a different branch internally where there was a completely different encoding of instructions inspired by the new Veil encoding. But that was unwieldy for other reasons for this. So we just stuck to the big, sum type, and then blasting it away in these pieces.
Cool, thank you. It's 12:30, so I think we'll wrap up. But thank you for the talk. It was really good.
Thank you.
Yeah, please feel free to ask other questions on the Slack channel, the F-Star Seminar Slack channel. Thank you.
Yeah, thanks, Jay.
Thank you.
Bye.
Thanks, Jay. That was great.
Thank you.